We are.
All right, so we got our 1.5 F2 sitting here, good old valve, PSV 16. We're going to overpressure the 200-gallon tank. The PSV is going to protect it. All of our pressures are below the MAWP of the tank, so don't worry. You can't overpressure it for real. We're going to go through our inlet line here. Starts off at 2 inches, wedges down to 1.5 inches, and then up through our relief valve. Right now, the piping is set up so that we have this loop that is interconnecting and goes on the piping. You might say that no loops like this would exist in a refinery, but if you have a relief valve on the top of a tower going into multiple condensers, you could very well have this setup. Granted, there would be different equipment down there. So let's go ahead and see if this is stable or not with the relief valve coming in and us having the whole loop open. All right, y'all, let's get the engineering information out of the way. We've got an inlet and outlet pressure loss less than 1%. I've got a blowdown of 6.3% and a positive force balance, as a force balance needs 5.2% blowdown to be neutral. And our inlet line length to critical line length is 0.61, so it's outside the range where coupling should occur. All right, so let's look at this chart. The traces, there's 2 traces. The bottom trace is the pressure directly underneath the relief valve, and the upper trace is the PSV lift. And both of these are relative, but you can kind of get an idea what's going on. In this picture here, the relief valve is opening. There's a little bit of a wiggle, but it's somewhat stable. And you can see that the inlet pressure is going up, and when the relief valve opens, the inlet pressure goes down, which is exactly what we would expect. I gotta turn my hearing protection on. Y'all don't have to. We're gonna give it about 70% of the capacity here. We'll get it popped and get the pressure going up a little bit, and then we'll let it go. Was a flutter. It was a low amplitude flutter. In a refinery or chemical plant environment, that would probably actually be acceptable. It was very small. Let me go ahead and swap this around. Close that valve off. What I'm going to do now is I'm going to open up this valve here, and now we have a dead leg off of this dead leg that ends here and here, so only this 1.5 to 2 inch section of pipe, maybe 5 feet long, is included in that. All right, so it's a little difficult to see what I've done in this picture, but I've basically opened up the green valve, which exposed the yellow piping to the system. That includes the 18-inch rise and then the 45 inches of other pipe. So that's 63 inches of pipe, so 5 feet is a pretty good estimate. So doing this changed the acoustics of the system, and as we'll see, that had a major effect on the system. I believe what's going to happen when I run this is that valve is going to be significantly more unstable. Let's go ahead and see what happens. So when you guys are watching this, up in the corner over here, we're going to have the printout from the data instrument, and you'll see that that was in fact way worse. So let me go ahead and we're going to run this. We're going to clip the loop off a little bit. I'm going to close it right here at this valve so that flow from the PSV is going to come around and up and in, and then we're going to have a dead leg that goes all the way around and back to here, and it's going to end here. Let's see what happens. If y'all have any predictions, write them in the comments. I think that'd be fun. Again, we're going to run about 70% of the valve's capacity for just a bit. All right, let me walk through. All right, so that was very interesting. Closing this valve made the amplitude of the vibration significantly worse than leaving it open. So let's go ahead and let's see what happens if we close this one. And so now all of the flow is directed this way, and we do have our dead leg coming around, but it stops here. But all the flow has to come to the relief valve this way because this valve is isolated. Pretty interesting. That amplitude was probably a little bit worse than this valve closed and that valve opened, but not nearly as bad as the whole thing opened. So let's try this. For kicks and grins, every test up until this point had a nice short inlet pipe to here, but I've now closed this valve. So now, in order for this valve to protect this vessel, it has to go all the way around the loop and out the relief valve. Any guesses as to what's going to happen? I think it's going to be absolutely fascinating. All right, so with this configuration, we have significantly more piping, 286 inches to be exact, or close. So, but we still have less than 3% inlet pressure drop because this is in fact a 1.5 F2, and it's a small valve. But the force balance predicts we need a 16% blowdown to be stable, and we only have a 6.3%. So that says we should be unstable. The critical line length is such that the actual line length, the critical line length is 1.8. So that is outside of the range of horrible connectivity. So it'll be interesting to see what this plays out as. Which you probably couldn't hear that. Absolutely fascinating because I was behind the tanks. All right, let me put my hearing protection on. Let's do this. It was completely stable. There's a little wiggle here and there, but it does not rise to our definition of chatter or flutter or instability. Now it's going to blow your minds. That was stable. If I open this valve and open up this portion of pipe, which does not affect the flow path, it's going to go unstable. Let's check it out. Those nuts are getting loose. All right, y'all. The crazy thing is, turning this valve and opening up this dead leg, which should make it better, actually made it worse. So what's absolutely fascinating about this is the valve that's covered in blue here. When it's closed, the PSV is stable. When it's opened, we access the green piping, which is about 5 feet as we talked about before, and that turns the stable valve completely unstable. And it's not in the flow path, and it's not in anything else. We still have the same failure of the force balance at 16% required blowdown, where we only have 6.3%, and we have a 1.8 actual line length, critical line length. But the thing is, we didn't account for opening that blue valve in any of these things, and it made all the difference in the world. Stable position for this relief valve of the 5 or 6 that we've tested is the most torturous path through without a dead leg. So when you're doing the force balance, consider that all of the non-flowing piping can have as much of an effect on your stability as the flowing piping. Have a great day.